about sampling, some new results of sampling and applications on learning and mining.
No new results, old results. Old work. Okay. So what's sample complexity? Why should you care about sample complexity? How it's relevant to what we're doing here? So it comes up under a large number of buzzword titles: data science, machine learning, data mining, pattern recognition, and more. But all these basically are doing, in the high level, the same thing. We are taking data, running some algorithm, and trying to fix a model or to predict a model. And of course, the model is measured by how good it is predicting results that come from the same distribution of data or the same world. Okay, so there's all these different areas that are doing it, and being a computer scientist, we usually focus on the algorithm. Okay, we look at the efficiency of the algorithm, we ask whether the algorithm is correct with respect to the input, and so forth. And in the context of data, we or the more practical people, even came out with this phrase, this is the best the algorithm can do with respect to the data. That's something you hear a lot in practical AI. But that's kind of the wrong way to look at it, because we all knew that this we heard for many years: garbage in, garbage out. Well, however good algorithm you have, if you don't give it the data, then you won't get the result. Okay, so what we're going to look here is not so much the algorithm, but when do we actually have enough data in order to find the information we're looking for? So if I want a model for something, at what point the data has enough information in order to create the model, or in order to fix a model or approximate the correct model? So we're not going to talk about algorithm complexity here, but we're going to ask a question, this is somewhat orthogonal, which is, when is it actually worthwhile to run an algorithm at all? When do I actually have enough data in order to get a result? Okay, so sample complexity try to address these fundamental questions. And in fact, the three questions are in fact equivalent, or different ways to ask the same thing. So when does the data or the training set contain sufficient information to make a valid prediction or to fix a sufficiently good model? Is the sample sufficiently large, or the training set sufficiently large? We use sample and training set here interchangeably. How accurate is the prediction that I can infer from a sample of a given size? Okay, that's another way, just another way to ask the same question. Now, interesting statistics. So you think that all this would have been solved years or almost a century ago by statistician, but as we'll see, the kind of questions, even if you phrase them in pure statistical modeling, the kind of question that you ask in learning are different than the standard question that I answer in statistics. Okay, I'll just throw the phrase here, and I won't get back to this. You can look, or the complication in learning is something that statisticians call the multi-comparison problem, and they have their own ways to look at it, which is, I will not talk about it here. But in a way, as you'll see, the complexity is we're asking many questions in parallel, and we want to answer them, all of them correctly, simultaneously on one set of data. And that's very different than your standard statistics that you learn where you ask one particular question. Okay, so what I'm going to do here, so I don't have much time to really cover everything that's listed here, so I'll kind of emphasize only things that are kind of more general and relatively different than what you'll study in your standard machine learning course. But we have to start with, the whole thing, of course, started with in the 70s by the VC paper. And so the motivation is learning binary classification and the distinction between the realizable and non-realizable case. So I'll talk a little bit about it just to have a concrete setting. And then from that, we'll get to this general idea of uniform convergence that is underlying everything we're doing here. Now, all this, of course, started with the VC paper, and the VC dimension is the first concrete method to prove uniform convergence. Although I realize that that's not the way we usually teach it in machine learning courses. So we'll talk a little bit about VC dimension. I kind of assume that if you sit here, you probably know something about VC dimension. I'll skip a lot of the technicalities so we can get to other stuff. But we'll talk a little bit about this. And again, I'm going to emphasize something that is slightly different than what we do in standard PAC learning. Okay, and then I'll talk about some applications of VC dimension. Then we'll go to a theory that is somewhat newer. So VC dimension is from the 70s. It's something that came up in the last 10, 15 years. In fact, there is a guy here in Berkeley, Barlett, that is a major player in this Rademacher complexity business. So we'll talk a little bit about Rademacher complexity. We'll see what it is. We'll see why it's different than VC dimension, why it's promising better, tighter results. And then I'll show, only very high-level discussion of some application of Rademacher complexity. Okay, and all this, hopefully, we'll see how much we can fit into the time. What's the take-home message? So obviously, all this uniform convergence is one of the most beautiful theories that we have in probability, in computer science, the double sampling idea, all this. So I hope that you get the idea, if you haven't seen it before, that this is really a beautiful theory. And it really started as a theory. The idea originally was just to show that there are concepts that can and cannot be learned by a finite sample. So that's like a very theoretical thing. But what I'll try to convey you in these 2 hours is that it's not just theory. And through a lot of work that was done by computer scientists, also in other areas, we actually now can get bounds, concrete bounds that are compatible with anything else that we can do, and can actually lead to even practical solution. So I'll try to convince you, not too many details, that this is more than just a theory. It's actually something that you can apply. You can actually get, real results out of this. And the last thing is, well, we usually associate VC dimension, Rademacher, with learning, but actually it's much more than learning. I'll show example from what people call data mining or data analysis. And of course, there are also applications now in privacy and security. So it's kind of the obvious complement. If I need this number of samples in order to learn something, then if I don't have that many samples, then maybe I cannot learn it. The complication, of course, is what I want to learn is usually not what I want to hide. And so there is, very interesting theory around that. I will not talk about it, but anyway, I just want to emphasize that all this is far beyond this binary classification that was the origin for all this. Okay, so here's the standard binary classification problem. So we have some unknown probability distribution over some domain, and there's an unknown classification that partition the domain into, say, the in and out sets. Okay. So a concept class, now, we of course want to learn, so we get some examples with training sets, which are examples from that distribution and their classification. And we want to be able to predict for a new element that come from the same distribution to predict their classification. If this was the problem, then it's almost hopeless. We won't get to this here. So together with this, we get a concept class, which is basically a collection of all possible classification that we'll take into consideration. Okay, so say we only look at hyperplane that partition the domain, or we only look at polynomials that partition, or we have some set, might be huge, might be infinite set of concepts, and we only choose between this set of concepts in our learning. So the goal, if one way to define it is that with probability 1 minus delta, we come up, our learning generate a classification, and that classification is correct with some error epsilon. And now what is correct? So we find a concept or a partition among all the possible concepts, all possible partitions that are given to us, that is up to epsilon from the optimal. And when we take, and this is the expected error, and the expectation is taking over the distribution of the input. Okay, so that's the standard binary classification. I'm sure that you saw it before. Okay, so in picture, what we have is we have the red and blue points, that the in and the out. We get all sorts of possible classification to choose more, and we want to choose a classification that fits as much as possible the truth. Maybe I'll skip one. And how do we know the truth? So we get these samples, and so if the sample here says that this is out, then I definitely would not choose this one as the in set. And if this one says it's in, then everything that include this can still be one of the in classification. Okay, so it's important for us to distinguish between two cases, and this would lead to the different definition of convergence, uniform convergence. So in the realizable case, someone tell us that there is a concept in our concept class that is perfect, that is consistent with all our training set. Okay? So in the realizable case, there is a concept in the set of concept class that is consistent with all our training set. It might be very hard to find it, might be exponentially hard to find, but there is such a thing. Well, so what do we need from the sample in the realizable case? Okay, so how good sample we need in order to find a solution or a concept that is very close to the optimal? Well, so the trick, of course, is we look at, for every concept, so let's, so let's see with the perfect concept. I notice it's different notation here. Let's see with the optimal concept. Let's delta of CH be all the elements in the domain, which I don't see all of them, in which they differ. Okay? So if I pick a sample in this set, then I will know that age is not the correct concept, because age would not classify it correctly as it says in the training set. Okay? So what do I need in order to find a good classification? Well, I need to have a sample that hits every set of these deltas. When you go over all the deltas for all the possible concepts, for each of these set that has probability greater than epsilon, I want a sample to hit such a set. Okay? So in other words, for every concept that differs from the optimal concept by measure epsilon, I want the sample to hit the difference between them. Okay? So in other words, what I need, and in that case, well, the probability that I make an error, if I choose this one, then there was no example in which, then if I chose this one, that means that there was no sample that showed me that this one is wrong, and therefore it has to be correct up to an error bounded by epsilon. Okay? Now, what's important here for what we continue, what we need later, is that what we need of the sample is to intersect every set among all the possible delta set that is not too small. So usually we say, well, how many samples I need in order to hit a set once? But now I have a huge collection of sets, possibly infinite collection of sets, and I need my samples simultaneously to hit each of these sets at least once. Okay? Now, the more reasonable model of learning is the unrealizable case, in which we are not guaranteed that our training set is consistent with any of the concepts that we know. There are two reasons for that. First of all, why would you know a concept set that includes the truth? You know, who gave you that information? But, yeah.
It's enough to have a low error rate.
Sorry?
It's enough to have a low error rate.
Yeah, okay. And yeah, okay, just a second. And the other one is the error. Okay, if you get real data, then you have noise. Okay, so yeah, if all the noise is guaranteed to be below epsilon, well, you're doing okay. But if you have at least one element, and if any of you work with practitioners, there are always some elements that are outliers. If you have one element out of that, then it's not consistent with this. Okay, so what do you do in the unrealizable case? Well, then you said, well, okay, so for each concept, I kind of look at the empirical error of that concept on my training set. Okay, and I want to choose the one that minimizes this empirical error. Okay, and so now we have that if our sample estimate correctly or estimate within epsilon error all the event delta CH, then we have enough information in order to find a concept such that its error with respect to the optimal is no more than well, actually I have to estimate each of them with epsilon over 2 in order to get error epsilon, or if I estimate all the differences by error epsilon, then I get something that the concept is correct up to error, or the concept is no worse than the optimal plus 2 epsilon error. Again, beyond the details, what I want you to get out of this is that what we need is, again, we need a sample. And now it's not enough that it hit every set at least once. We have a collection of sets. Again, it might be infinite collection of sets. It's the difference between all hypotheses and the correct hypothesis. And we want our sample to estimate within epsilon error the size of all these sets uniformly. Okay, so we need a sample that simultaneously estimate the probabilities, or the ratio of the sample that fall into this set is proportional to the probability of these sets up to an epsilon error. Yes?
I thought we defined the class of C and the H and C to be the ones that agree on the training set with C.
No, that was the realizable case. Okay. Now we have the unrealizable case. There might not be a concept that actually agree with our training set. Hopefully there's a concept that... so in fact, there might be no concept that agree even on most of the training set. We still just want to find the best concept that we have among all the concepts that are available to us. Okay? Okay, so this brings us now to the definition of the uniform convergence. Come from the VC paper long before we knew about machine learning. This is in the 70s. Okay, so assume that we have a set of function. We say that the set of function, and this again can be an infinite set of function or finite. We say that the function has the uniform convergence property with respect to a domain Z if there is a function that is a function of the, well, if there is function M that is a function of the family of our function or concept, n epsilon delta, such that this function for every epsilon delta is finite. And this is going to be the size of our sample. And such that for any distribution D, and that's the important part here, every distribution D on our domain, And any sample Z1 to Zm, well, this is the M, okay? If we have this sample, then with probability 1 over delta, our sample estimate, so these are empirical estimates of the expectation of F. This is the actual expectation of F, okay? Now we look at the maximum over all, or the sup over all the function, and we want this to be bounded by epsilon. Now, before we talked about expectation, before we talk about probabilities, now we talk about expectation of functions. So obviously, if I can estimate the expectation of function, I can have the characteristic function of each event, and its expectation is the probability of that event. So I'm actually just generalizing the previous requirement. So again, what I have now is I have a set of function, it might be infinite, and I want the property that for any epsilon delta, there is a finite value m, such that if I take a sample of m, items from that distribution, and I look at the empirical expectation of each function, you know, the difference between this and the actual expectation of the function in that distribution, the sup over all the function is bounded by epsilon with probability 1 minus epsilon, okay? And this I want for any distribution D. Okay. Why this is what I want for learning? So think about f as the loss function. Okay, so loss function, even if you don't know, it's the penalty you have for making the wrong decision. So in the simple binary case, it's 1 penalty if you have the wrong answer and 0 penalty if you have the right answer, but it can be, you know, any function, and often you use different functions. So if f of h is now the collection of all the families of a penalty with respect to all the hypotheses, okay? Now, if fh has the uniform convergence property, that means that I can take a finite sample and I can take I can run, at least conceptually, we don't talk about the complexity of this, but I am looking at the empirical risk minimization. That means I find the concept that has the minimum error or minimum loss among all the errors that I have, among all the concepts that I have. And if if this is a uniform convergence set, then I have a very good estimate for the error of all the concepts. Okay, and if I take the minimum one, then it's actually this, according to Vapnik, this is actually the definition of being able to learn a concept class. Okay, so if I can use a finite sample in order to identify the concept in the set of concepts that has the minimum error. Okay, and so the function m as a function of the set of function fh is the sample complexity of the problem. Okay, so now so that's basically how or why uniform convergence is the underlying theoretical property that you need in order to learn. Okay, or in other words, you can actually, if you look at the way Vapnik writes it, this is kind of the definition of learning. Okay. Okay, now you wonder, now all this of course was completely, mostly ignored until the 84 when Les Valiant came with the pack learning idea. And the pack learning basically set this in the computer science setting where we actually asked that the learning will be done in polynomial time. And this led to, rich theory of, learning. Okay, but in terms of the sample complexity, this is all goes back to Vapnik work. Okay, so so this was kind of the introduction about what is uniform convergence, and now we'll move to how do we achieve uniform convergence VC dimension, first example, Rademacher complexity with the other example. By the way, there are other techniques to do it, but they're all in the, well, I'll talk about it later, they're all kind of in the same setting of the VC dimension, not the Rademacher complexity. Okay, let me just put all this in some background, which might actually clarify some point to some people. So assume that we have a Z1 to Z1, a ZM sample from some distribution. And so this is the empirical distribution function that we take from the sample. Then the strong law of large number tell us that for any given x, the empirical distribution for x will converge to the value of the distribution at x. Okay? So that's the law of large number. Okay? The Cantelli or the Gilvenko-Cantelli theorem is the first one that build uniform convergence, but only for this set of events. Okay, so the set of events corresponding to the probability distribution, for probability distribution, and they show that this is has the uniform convergence property. There are a lot of theorem of this form, but if you come from Jerusalem, that's the Dvoretsky-Kiefer, Wolfowitz, the one you know. So this basically shows that the uniform convergence can actually be translated to a large deviation bound of the form that we need. But again, this is just for the set of events, okay, that correspond to, to a distribution. So putting it in the setting, this kind of pure mathematics setting, what the VC dimension is doing is it tried to characterize other set of events or function that have this uniform convergence property. So this is where, what we are doing fits into the general setting of probability. Yeah.
What's n in the Dvoretsky Upfal? If you look at
sorry.
I think it should be.
Oh, it's n. It's m. Sorry. M. Sorry. Other question? Okay. So so we all know one way to get uniform convergence. That's union bound. Okay. So if if I want to be able to hit every event of probability epsilon, then I can have a sample of size that is proportional to the number of concepts plus the error, and obviously I hit all the concepts. So the probability that I don't hit one of them is 1 minus epsilon to the m, and then I take it over all the possible concepts, and I get, bounded by delta. Okay. So why union bound doesn't help us, or why doesn't it solve a problem? Well, I don't have time to get into detail, but I think you all could realize that we can easily learn an interval with a finite number of samples. So what does mean learning an interval? So assume that we have a distribution over the line, say a bounded segment between A and B to make it easy. And there is some true classification, little a, little b, which is an interval on the large domain. And our concept class are all the possible interval. Okay, so we have infinite number of concepts, and it's not hard to see that we can actually learn the correct concept by finite sample that is just a function of epsilon and delta. So basically the trick is that assume that AB is the correct concept, define interval here and interval here, each of them with measure epsilon over 2. Okay, so if my error, so here are the examples that I see as positive. These are the examples I see as negative. My algorithm just take the interval that include all the positive example as the in. Now, if there is an error, and again, BA is the real interval or the correct interval, well, if there's error more than epsilon, then there is some interval epsilon over 2 here and epsilon over 2 here that we missed, and in our training set. And so, of course, a finite training set, which the size is just a function of epsilon and delta, would give me that. Okay. So what happened here? Before we needed, our union bound could only work in finite number of concepts. Here we're in finite number of concepts, as it's so easy to learn. Well, so each sample here excludes many possible intervals. So if I have this negative example that I know that all the intervals that include this one are excluded, the union bound, of course, sum over overlapping of hypotheses. So we need something much better, much smarter, in order to figure out how many samples we need. Okay, that's the proof. Okay, so we switch to the second. So I will talk a little bit about VC dimension. I'm going to skip a lot of the proofs. It's all here. It's all in the deck. If someone asks me, I'll be happy to, but we don't have time to cover all this. I want to get to new material. So just remember that for the realizable case, we needed the following property. We needed that. So now we think about it in a more abstract thing. We have a collection of sets over a universe or over a domain. And there's some distribution defining over the domain. For the realizable case, we needed the property for any set R such that the probability of R is greater than epsilon, where our sample intersect R. This is what we call an epsilon net. And for the unrealizable case, we needed that for any R, we can estimate or the ratio of the intersection of our sample with R. Okay, well approximate the probability of R, approximate within epsilon. We call this the epsilon sample. Okay. Now, usually, because of PAC learning, we talk about epsilon net, but for application that are beyond, the machine learning, we're actually really interested in the epsilon sample. Okay, so I'm going to talk a lot more about the epsilon sample, also assuming that some of you already saw the epsilon net results. Okay, so, but just to remind you, what's a VC dimension? So VC dimension abstract the whole thing. So we have a domain, we have a collection of sets, which we'll call ranges, just so we don't use sets all the time. X can be finite or infinite, R can be finite or infinite, and R is just a family of subsets. And the important thing in VC dimension is the concept of projection. So let's fix a set S out of the domain, and now S is finite. Okay, so the domain can be infinite, but now we fix a finite set. And now we ask, if I look at all the ranges, but I restrict them to the set S, how many different ranges we actually have? Okay, so I can start with a finite number of ranges, but if my set is finite, then many of the ranges, when they are projected or the finite set, either coincide or are completely not there, or so forth. So I ask, how many sets are in the projection? Okay. So now, if the projection on M element, if the projection has 2 to the M sets, that means every dichotomy or every subset is represented in this projection. Then we say that R shatter S, and in putting some motivation, it means that the projection already already represent all the possible dichotomies of the set S. So, okay, so now the VC dimension is basically the maximum size S that is shattered by R. Okay, now, it's not every set of that size will be shattered of R, but we're looking at the maximum size of a set, or the set of maximum size that can be shattered by R. So this is the VC dimension, And if there is no such limit, then we say that the VC dimension is infinite. And as I mentioned before, the initial work really was focused on the fact that there are sets that have, or there are a concept class that have infinite dimension, but we now really are interested in really evaluating the VC dimension. Okay, I assume most of you know about it, so let's just take two examples. So, if I look at intervals, so this explains why we can study interval so easily. So if I look at intervals on the line, so I easily can shatter two elements. So there's an interval here that would cut it to two. There's an interval that would include most of them. There's an interval that includes this one. And there's an interval that doesn't include any of them, so that I can shatter a set of two. But there's no way I can shatter a set of three, because there's no interval that will include the two red point, doesn't include the blue point. So interval on the line have very low VC dimension, and we see later that the VC dimension actually give you the size of the training set that you need in order to learn it, which will explain the example we saw before. If you look at a half space on the plane, then you can shatter every 3 point. There's no way you can shatter, you can distinguish between, or can separate the two red from the two blue. So the VC dimension of half plane is 3. And just that you don't get the idea that every simple example has a small VC dimension. So if we look at all convex bodies on the plane, in fact, it's enough to look at all polytopes, then this concept class has infinite VC dimension. Why? So I can put any number of points in a circle, and I can identify any subset of these points, and I can connect them or include them in a polytope or in this structure, and not include the rest of them. Okay, so I can basically shatter any set of points for any size using convex bodies, and so this concept class has infinite VC dimension. Okay. So the important application now is that if you tell me the VC dimension, I can tell you how many samples I need in order to estimate the probability within epsilon arrow of all the ranges in a range space. Okay. So again, this is the epsilon sample theorem. There is a similar theorem with the square here is eliminated for the epsilon net. But for the application we need later, this is actually the more important theorem. This is what allows you to use this for other data mining or other data analysis problems. Okay, so the important thing to notice is that the size of the sample is a function of d, epsilon, and delta, but is not a function of the size of x, and is not a function of the size of r. Okay, so although I am estimating simultaneously the probabilities of infinite number of ranges or sets, okay, the size of the sample I need is only a function of the VC dimension, and the error, it's not a function of the number of events or the number of sets that I'm estimating. Okay. This is, by the way, not the tighter result you can get. You can get a slightly better result using something called chaining, but I really want to spend 2 minutes on this beautiful theorem. So that's maybe the only proof I want to go through. So this is one of the most beautiful and tricky proof. This is the double sampling idea. Oh, sorry. So before we get to the proving this theorem, there is this technical result, which I won't prove here because the proof itself is just by induction, but this is actually where the real value of VC dimension comes from. It's known as the Sauer lemma, but for those who come from Jerusalem, it's the Sauer-Shelach lemma. And I mention it in case someone from the other logic program is here to show that all this is actually related to logic as well. Okay, so if we have a range space of dimension D, and if we take a subset S of size M, then we ask, well, okay, what's the size of the projection of our range set on that sample? So we know that if the VC dimension is D, then the projection of D elements is 2 to the D. I mean, that's how we define a VC dimension. Okay, we said there is a set D, such that the projection on D has 2 to the D sets. Okay, but the important thing of the Sauer lemma is that as we go beyond D, the size of the projection grows not exponential, but polynomial. So it goes polynomial in D. Okay. So this is the crucial way we're using the VC dimension. Up to D, or if we have D element, then the projection is 2 to the D. And if we get a larger set of elements, then the projection on that set has only M to the D different sets. And jumping ahead to the punchline of the theorem, what does it says is that if you look at the sample has only to deal with, not with all the possible ranges in the world or in the range space, but only with this number of ranges. Because on the sample, these are the size of the projection, or bound on the size of the projection. Okay, so I have what, 5 minutes? Okay. Okay, so when I teach it, it takes a whole hour. So, but the idea here is just to show you the cleverness of this technique. And most people, the first time you see it, you don't really get, the deep idea. Okay, so how do we prove the epsilon sample? So here is the event that we want to bound. Okay, so we choose a sample of size M, and we want to bound the probability that there is a set R that is not well approximated by our sample. We want to show that this is bounded by delta. So now we choose another sample, not clear why. And now we want to estimate somewhat more complicated events. So we don't know how to estimate this one, so we define an even more complicated event, and we try to estimate it. So now we want to estimate the probability that, well, the first sample was bad, but the good sample is good. Okay, what does meaning good? Well, for that set for which, or for those sets for which the first sample failed to estimate them correctly, the other sample estimate them properly. Okay, so remember that these fractions, the probability of R, is P of R, so this function is supposed to be closer to P of R. Okay. So now, obviously, the probability of this E2 is smaller than probability of E1 because it has another restriction. But this restriction is kind of trivial because that's what we expect, okay, from a sample to have. So we'll formulate it by showing that the probability of E2, okay, is, or the probability of not satisfying E2 is, so P2 is just, is that, okay, that the probability of E1 is bounded by twice the probability of E2. Okay, so the probability of E2 is not that much smaller. Okay, so remember again, E2 is smaller, but it's not that smaller. Okay, it's no more than twice. Okay, so I'll skip the detail here, but so how do we prove this ratio? Well, we look at the ratio between this probability. That's basically the probability of E2 condition on E1. Well, what's the probability of E2 condition on E1? Well, it's the probability that there is a set that was not estimated well by the first sample, but is estimated well by the second sample. Well, the probability that there exists such a set, well, it's definitely greater than the probability that one arbitrary set will have this property. And again, since this is what we expect from the sample, this is high probability. It's probability at least half. So we are done. So we get this ratio. Okay. So now we define a third event, which is kind of simplification of E2. So it's E2 prime. So remember, here we say the first sample miss the right probability by more than epsilon. The second sample is within epsilon over 2 of the right sample. So now we want that there is any set R such that the difference between its intersection of n with n and its intersection with t is greater than epsilon 2m. Okay, so remember this one is the intersection is greater than epsilon n. This is smaller than epsilon n over 2, so the difference has to be this. So this one is more general than that one. Okay, and this is formal proof for that. Okay. So now we want to show that now we're getting to the punchline. Okay, so we want to show that we can actually bound the probability of this event. Okay. So now we said, well, we had one sample and then another sample, and one sample we had some property, and the other sample had other property, but they're both samples. So we could as well just take one sample of 2m elements and partition them to 2 samples. Okay, now I can partition them any way I want as long as I don't look at their values. So it's going to be easier to do the following partition. So assume that I take Z and it has 2m elements. Now for each pair Z1, Z2, Z3, Z4, and so forth, with probability half, we either switch their order or not. Or with probability half, the first one go to N, and the second one goes to T, or with probability half, the first one go to T, and the second one go to N. So basically, I partition the Z into 2 sets by taking any successive 2 and randomly assign one of them to N and one of them to T. Why we do it, you'll see in a second, it fits into a channel bound. Okay, so now we get to the punchline. Okay, so now we look for one particular set. And we ask what the probability that we get this property that R intersection of N is much bigger than the R intersection of T. Okay, if I have this probability, then the union of this is the event that I want. But now, what happened now? We have a set of elements, and we partition them randomly to 2 subsets, and we ask whether one subset intersection has large intersection with R, the other one has small intersection or so far, or the opposite, okay? The event now has nothing to do with the original set Z. I could choose any set of elements, out of my domain. The probability now is only about the partition of the 2m elements into 2 sets of m. Okay? So again, I have a set of 2m elements, and I ask what happened, what's the probability that when I partition this 2m into 2 sets of m, one of them has large intersection with R and the other one has small intersection with R. This probability has nothing to do with the way I chose Z. I can have worst case Z, arbitrary Z. The only thing now is a probability on the partition. Okay? So now I got rid of all the setting, of all the range space setting. I'm just asking a question about a particular set Z. Okay? Okay, so now basically what? I have plus 1, minus 1 in the partition, in the splitting. So now I look at the pair. Either both of them are in R. It doesn't matter how I assign them. Either both of them are not in R. And again, it doesn't matter how do I assign them. Or one of them is in R, one of them is not in R. And so there's probability half-half that I put this in N or in T. Okay? So now this, what's written here is basically a sum of plus 1, minus 1 independent random variables with probability half-half, and we know how to bound it using a Chernoff bound. Okay? So for a particular set, the probability that I have this property that I split it in such a way that there is many more elements of R in one of them than in the other one, okay, is just reduced to the sum of plus minus 1, with probability half-half, and I have a bound for that. Now this is a bound for one particular set, and now I use the Sauer lemma to say, oh, but on my set Z that has 2m elements, there are only 2 to the m to the d sets that I have to consider. Okay? So the probability of the event E1, which was bounded by twice the probability of E1 prime, this bound by twice from the 2 here. This is the number of elements I have in Z. To the d is the number of sets. The number of sets are the size of the projection of R on my sample. And these are the number of sets that can be partitioned correctly or not. And for each of them, that's the probability that it partitioned wrong. And now there is quite a bit of arithmetics to show that this bounded by delta translate to this kind of MM, and we'll not do it here. Okay, so that's the proof of the epsilon sample, or that's the high-level proof of the epsilon sample. And okay, so we'll take a break, and then we'll get back to this. We'll see the application of this.
So we come back at 10:15.